Have you ever tried to fix something, make a little tweak, and ended up making the whole situation way, way worse? Well, that's exactly what we're talking about today. And we're going to explore this whole conundrum through the, believe it or not, fascinating world of turfgrass science. We're about to see how a step that seems totally logical can go completely and spectacularly wrong. So think about it. We all use filters on our phones, right? To make our pictures look better, a little more crisp, maybe make the colors pop. But what if we could use that same idea for science? Could a simple color correction turn a regular, everyday camera into a legit scientific instrument? That's the big question here. And look, this isn't just some weird thought experiment. Researchers are actually doing this. They're using affordable cameras, in this case, GoPros, to measure really important stuff, like how healthy plants are or how much ground they cover. It's a fantastic idea, a potentially super cheap and fast way to get tons of data. Now, the assumption they started with seems like a total no-brainer, right? If you're going to compare a bunch of photos, you have to make sure the color is consistent. You've got to strip away all the weird effects from the lighting so you can see what's really going on. I mean, it's the obvious first step. Of course you have to do that. So with that very logical assumption in mind, a group of researchers set up a pretty straightforward experiment out in the field to prove it. Okay, so here's what they did. Super simple, really. They went out to some grass plots on a partly cloudy day, and they took a bunch of overhead pictures. At the very beginning of all this, they took a picture of this special color checker card. Then they used that one photo of the card to create a correction filter and slap that same filter on every single picture they took. And this little guy, this is supposed to be our hero. Each one of these colored squares is a known, super precise color. So when you take a picture of it, you can basically tell your computer, hey, see the square? It's supposed to be this exact shade of green. And the software adjusts the entire photo to make it so. It's the ground truth, the one true reference for all the other images. But, and you knew there was a but coming, when they actually processed all the data, something really weird happened. The color correction didn't just tweak the data. Oh no, it completely changed it. Now, to our eyes, the difference is, well, it's pretty subtle. On the left, you've got the original picture of the grass. On the right is the corrected one. Okay, yeah, it looks a little warmer, maybe a bit more yellow, but it's not a huge, dramatic change, is it? But here's what the computer saw. These images show only the pixels the software decided were green grass. In the original photo on the left, you see a pretty solid patch of green. But on the right, after that tiny little color correction, a huge chunk of that green has just vanished. The software just doesn't see it anymore. How much vanished? In this one single plot, that simple color correction led to a 23% reduction in the measured green cover. Their attempt to fix the data made nearly a quarter of the grass just poof, disappear from the analysis. And this wasn't a fluke. Across the board, the average green cover dropped by almost 26% after they applied the correction. So where did it all go? Well, the software just reclassified it. It took all that missing green and said, oh, that must be dead yellow grass, or nope, that's just dirt. So you can see the problem here. This is a huge mess. The whole point of this was to get closer to the truth, not to create some completely different story. So now they had a big question to answer. Which data is actually right? Just think about that for a second. The one step you took to make everything better, more objective, just gave you a totally different answer. So what do you do now? How on earth do you decide which one to trust? Well, to find out, they needed a tiebreaker, an independent judge. And for that, they turned to something called NDVI. You can just think of it as a gold standard health scan for plants, often used by satellites. It's a super reliable way to measure vegetation. They compared both sets of their photo data, the original and the corrected, against these NDVI readings to see which one was actually closer to reality. And the results were a complete mess. I mean, on the one hand, the correction actually helped for some things. It made the data line up better with NDVI on a couple of metrics. But, and this is a big but, for other super important metrics like the greener area, the correction made the data way worse. The correlation just tanked by 32%. It wasn't a clear win or a clear loss. It was just confusing. So what in the world was going on? How could a standard procedure make the data better and worse at the exact same time? Well, it turns out the culprit was hiding in plain sight, literally, right above their heads. And the researchers themselves put it perfectly in the source material.
The weakness of the color correction may be due to the partly cloudy condition where one color reference image is used to correct all field images.
And here it is. This was the sky that day. It was partly cloudy. And what does that mean? It means you have sun, then a cloud, then sun, then more clouds. The light hitting the grass was changing constantly. The color of the light itself was different from 1 minute to the next. And that right there is the fatal flaw in the whole plan. They used one picture of that color card to create a single, constant correction, but they were applying that constant rule to a totally variable situation. The light in picture number 1 was different than the light in picture number 5, and that was different from the light in picture 20. Trying to fix all of them with the same tool didn't standardize them at all. It just messed them all up in different ways. And this leaves us with a really important lesson that goes so far beyond just taking pictures of grass. It's a huge reminder that any step we take to process data, no matter how logical it seems, carries its own set of assumptions. And if those assumptions don't match the real world, you can get into big trouble. It forces us to always ask that critical question: when does our attempt to improve our data actually end up making it worse?